Hello, good morning everyone. So today's lesson is on 5.2, graphs of irrational functions. From the previous sections, the reciprocal functions that we did on 5.1, we all know that a reciprocal functions in fact is a type of irrational functions because it is a fractions, okay? 1 over x is a fractions. But in general, the definitions of a rational function is f of x is equal to p of x over the q of x, where the q of x, the denominator, cannot be equal to 0, but both the p of x and the q of x, they are polynomial functions. So if you look at the reciprocal function, like the parents functions of the reciprocal y equal to 1 over x, you can say, how is the numerator, the p of x, now is equal to 1? So the q of x is equal to x. So how are they polynomial function? Yes, in fact, it is a polynomial functions. The p of x, the numerator, is in degree 0 because any degree 0 will give you a constant. So that's why the 1, in fact, is a degree 0 polynomial functions. And the denominator, the cube of x now, is equal to x. So x is in degree 1. So the reciprocal function, in fact, is a degree 0 divided by a degree 1. Okay? And if you look at more example, so if you have a y equal to 2x over x cubed plus 8, so this is another example of the rational function because the numerator is in degree 1, but the denominator is in degree 3. So this rational function is a degree 1 polynomial function divided by a degree 3 polynomial functions. Okay? One more example. When y is equal to a degree 4 divided by a degree 2. Okay? So this is all example of rational functions. There are a couple of things that we need to keep in mind when it comes to how to graph the rational functions. Because the natures of the formats of the rational functions in terms of is a fraction, so it makes it very difficult for us to get some of the key points to do the graph from the table values. So using the table values really is our last resource, like unless you have no other ways of how to get some key points. Otherwise, we will never use the table values, okay? So some of the things that we'll be talking about is, let's start with item number 1. Okay, the things that, some of the rules that we need to keep in mind. A functions will have a whole at x equal to a if both p of x and q of x contain a common factor, x minus a. Okay, so let's look at example number A, okay, from the handouts. Okay, if you have the handouts like this one, I want you to print it out so you can follow my example A over here. Okay, I'm going to do 2 examples and show you how to graph a simple rational functions. But before we start graphing it, we want to make sure that whether there is any common factors, from the equations. So first of all, if you get a degree 2 divided by degree 1, like example A, you always turn everything into a factor form. So x squared plus 2x minus 3 becomes a bracket x plus 3 times x minus 1. Okay, so you make sure that you factor this properly. Okay, because if something's wrong here, if you don't factor it correctly, then you will be getting the wrong 0 later on. Okay, so you always double check that you factor it properly. And when you turn everything into the factor form, a fully factor form, in this case, you will see that there is a common factors, x plus 3. Okay, there is a common factors, x plus 3. So when it comes to the simplify of the equation, you know that you can cross that off because they're common, so you can reduce it, right? So finally, this questions, you will end it up with the final answer of x minus 1. Okay? So f of x now, after you simplify, it becomes x minus 1. Because of the common factors that you have reduced before, the x plus 3, so x plus 3 in the form of x minus a, therefore, there is a hole at x is equal to negative 3. Okay? So according to the rule, we know that there will be a hole at when x is equal to negative 3. And how does that look like on the graph? Well, because after we reduce everything, the functions is only left with the x minus 1. And we all know that x minus 1 is a line, is a linear. So I am going to graph this line, x minus 1, okay? So using a slope or a y-intercept, okay? If you look at over here. And so the 0, if x is equal to 0, you get a minus 1. If x is equal to 1, you get a 0. And if x is equal to minus 1, then you get a minus 2. So, I mean, you don't need 3 points, but 2 key points with the y-intercept or the x-intercept, you should be able to draw this line, okay? So this red line here is a y equal to x minus 1, okay? However, because of the, there is a factor that we reduced that before, okay? And that will create a hole at x is equal to negative 3. So what happened in this line here? When x is equal to negative 3, okay, when you sub in a negative 3 here, you know that the y value is equal to negative 4. So at this point here, negative 3 and negative 4, this is where the hole is happening on the line, okay? So you still get a line, y is equal to x minus 1. But throughout this, in order to determine the domain, okay, the domain for this line, x minus 1, is no longer xer. Well, you start with the xer, but you will say x just does not equal to negative 3. Okay? And the range is no longer a YER, where usually the linear will have only the YER, but now the y just cannot be equal to negative 4. Okay? So this is what we should be observing every time when we trying to graph irrational functions. Okay? If, let's look at one more example over here, example B, okay, where we have this functions is already in factor form, which is good. So that saves us a little bit of time. And it has a 3 factor here. So it has x minus 2, x minus 4, and x minus 3. So this is going to be a degree 3 polynomial functions divided by a degree 1 polynomial functions, okay? So it's a degree 3, it's a cubic functions divided by a linear, okay? In this case here, again, we can see that there is a common factors, and this common factors is at x minus 3. Sorry, I should be using a red color here, so you can see that. So I'm reducing x minus 3. So what this equation will end it up to be just a x minus 2 and the x minus 4. Because after we reduce the x minus 3, the x minus 3 is no longer there. So at the end, we know that there will be a hole at, well, because x minus 3 in the form of x minus a, then x must be equal to 3. So the hole is happening when x is equal to 3 there. Okay? So what are we going to graph now Okay, this functions after we simplify everything, so it ended up to be a quadratic. So x minus 2, x minus 4 will have a 0 at 2. Oh, sorry. Did I write the questions wrong here? So the original question here, this one should be x plus 4. Okay? So, yeah. Apologies. So I wrote the questions wrong to start with. Okay, so now we know that this quadratic functions is x minus 2, x plus 4. So we should have a 0 at positive 2 right here, and a 0 at negative 4 right there. Okay? And with the 2, 0, we can figure out the vertex. The vertex basically is the x coordinate of the vertex will be the midpoint between the two zeros, which is a negative 1. Okay? So 4 here, 2 here, the middle will have to be the negative 1. Okay? When you sub in the negative 1, into the functions, so negative 1, negative 2 will be a negative 3, and a negative 1 plus 4 will give you a 3. So the y coordinates of the vertex will be a negative 9. Okay, so this is going to be your parabola, and knowing that the a is equal to 1, so you can pretty much get the other two key points, okay, so which is a 0, negative 8, or negative 2, negative 8, okay, by going to the step pattern, okay. And when you connect all of this point, and you will have to make sure that there is a hole when x is equal to 3. Well, when x is equal to 3 over here, then you get a 1. And when x is equal to 3 over here, you get a 7. So the y value when x is equal to 3, then the y is going to be equal to 7. So there is a hole at this point here at 3, comma 7. Okay, so this is the parabola, but with a hole. Okay, and because of the common factors that they have. All right, so those are the two examples that you can see where when the rational functions will have a hole on the graph. Okay.